All right, hello everyone. Welcome to the 8th talk in our EFI series. Our speaker today is John Steele, who's professor of math at Berkeley. Well known for his work in intermodal theory, core model theory, as well as many other areas of foundational significance. And he's going to be talking to us today about 3 staircases.
Okay, thanks very much for the chance to talk today. Without further ado, there's the triple helix. As you can see, 3 staircases. They're golden, and there's a white light at the top. Here's the overall plan. I'm going to talk about something called the interpretability hierarchy or the consistency strength hierarchy. And then among the different interpretations of the language of set theory that this hierarchy exhibits for us, we'll suggest that there might be a preferred interpretation and ultimate core model. This is the same thing that Hugh Wooden calls ultimate L. I'm using the letter K as a sort of tip of the hat to Ronald Jensen, who had something to do with this idea, but it's Hugh's ultimate L. Okay, and then we'll see that ultimate L is one hierarchy of sets within a group of 3 that are very closely related to one another, and such that one really seems to need to understand all 3 together to understand any of them. So that's what I'm calling the triple helix. And then we'll look at some potential axioms which tell you which of those staircases you're on, basically. And then some basic open problems. Now, I wasn't sure about the technical level. It's going to go from very general to very demanding. I hope that the things that you have to have a good deal of prior knowledge in intermodal theory or forcing to really understand, you will take at the level. I hope they'll be presented at some level where they're accessible. And I believe that with a few additional words, anyone with some experience in set theory can follow those ideas. So I hope that if it gets too demanding or too technical, that you'll prompt me to supply those additional words. Okay. Of course, it's math, and at the end, you can't really understand it unless you take some courses in set theory. But you can get an overview of how things fit together, and without that, so. Hope that this will help. Okay, the interpretability hierarchy. Okay, so for T, a first order theory, and I'm thinking of theories in the language of set theory, which are meant to be foundational. It's a remarkable fact discovered by Zermelo and Russell and others, that all of mathematics can be expressed in the language of set theory, and all of mathematical theorems can be proved from a certain list of axioms about sets called Zermelo-Fraenkel set theory. So For me, in this talk, a theory is a theory in the language of set theory, and they all extend those basic Zermelo-Fraenkel axioms. Those axioms are incomplete in basic ways, like they don't decide the continuum hypothesis, and that's our problem. It's been the problem of set theory since Cantor. Okay. With that, let T be a theory. The arithmetic of T is the set of consequences of T in the language of first-order arithmetic. So you're in that language, you can only quantify over the natural numbers and say, talk about addition and multiplication, for example. Okay, so those are very concrete consequences of this very abstract theory. Okay, now it's a phenomenon that if T is a natural extension of ZFC, then there is an extension S. Somehow the slides are off center. Is there? It's not going to help, I guess, if I move my laptop. That's the extent of my ability to fix it. Let's see. Okay, then there's an extension. So if you have a natural extension of ZFC, then there's an extension axiomatized by large cardinal hypotheses or strengthenings of the axiom of infinity. The existence of an inaccessible cardinal is one example. Large cardinal hypothesis, such that S and T have the same arithmetic consequences. Okay. Moreover, if you take two natural extensions of ZFC, then the arithmetic generated by one is included in the arithmetic generated by the other. They're comparable. So there's a linearly ordered hierarchy here. In fact, well ordered. Okay, the kicker here is natural. What do we mean by natural? It's not a theorem about arbitrary axiomatizable extensions of ZFC that their arithmetics are comparable and certainly can be incomparable. But any theories that set theorists have seen any reason to come up with on their own account. And it's, there are hundreds of thousands of papers, hundreds of thousands of pages written in set theory, no doubt. And what set theorists consider as an interesting property of sets to look at is quite liberal. So this is a significant phenomenon. Okay, in practice, the arithmetic generated by T is contained in that in U, just in case Peano arithmetic proves that the consistency of the stronger theory implies the consistency of the weaker one. So the ordering on arithmetic consequences coincides with ordering on consistency strengths. Okay, now let's go up from the theory of natural numbers to the theory of sets of natural numbers, or real numbers. So for T, a theory in LST is the language of set theory. For T, a theory in the language of set theory, the one arithmetic, which is the second order arithmetic of T, is a set of consequences of the form V omega plus 1 satisfies phi. You can think of V omega plus 1 as being the power set of the natural numbers together with some reasonable additional structure, if the notation's not familiar to you. Okay, or the real numbers with some additional structure. Okay. Okay, now we have the following generalization, the prior phenomenon. If S is a theory, is the theory ZFC plus there are infinitely many wooden cardinals, so a certain large cardinal strengthening of ZFC, then if we look at theories which extend S, in fact, just such that they're consistency-wise as strong as S, let T and U be natural theories such that the arithmetic of this fixed S is contained in their arithmetics, then either the second order arithmetic of T is contained in that of U or vice versa. Okay, we can summarize this that at the level of sentences about V omega plus 1 or the power set of omega or the reals, we know of only one road upward. We are led to this road in many different ways. That is, there are many different of these set theories. These abstract superstructures. But at the level of consequences about the reals, they line up. Okay, so we're led to this road in many different ways. Strong axioms of infinity are its central markers. Now, the continuum hypothesis itself is a sentence one type up. It says, is there a set of reals with some property? It doesn't just talk about reals, it talks arbitrary sets of reals. Okay, so, okay, so some remarks. First, it's really not linearity that's so important, but directedness, that you can put any two of these theories together. They don't contradict one another. That's important for a well-determined theory of V omega plus 1. Okay, the phenomenon extends to beyond sentences about V omega plus 1. We can talk about not just about reals, not just about arbitrary reals, but about well-behaved sets of reals. And the well-behaved sets of reals are the Hom infinity sets of reals. I'll give you a precise definition later, but just think of Hom infinity as being the well-behaved sets of reals. They're all a big measurable. For example, there's no well-ordering of the reals that's Hom infinity. These are the well-behaved sets of reals. So what you can say, so if you look at sentences of the form, there is a well-behaved set of reals such that something, where the something now just has real quantifiers, then those are the sigma 2-1 Hom infinity statements. The consequences of our natural theories are linear on those statements. Okay, the higher up you go in the consistency strength hierarchy, the more and more of those you prove, and there are no contradictions between different natural theories. Okay, now Levy and Solovay showed some time ago that that the phenomenon does not extend to arbitrary statements of a form. There is an arbitrary set of reals with some property involving real quantification, because this continuum hypothesis is of that form, and large cardinals don't decide the continuum hypothesis. That is, so the phenomenon does not extend if the way we've climbed the consistency strength hierarchy is via conventional large cardinal axioms. So there's another sort of element of, I'm just pointing at the conventional ones and saying they don't decide, because they have a property called being preserved under small forcing, and that means that you can take any interpretation of the language where you have your large cardinal axiom and CH is true, and morph it into one where CH is false, and you still have the large cardinals. And similarly, if you start with it's false, you can make it true and still have the large cardinals. Okay, so if the way we climb the consistency strength hierarchy is by the conventional large cardinals, we can't decide CH that way. Okay, so there may be large cardinal notions beyond our conventional ones. We're going to stick to the initial segment of the consistency strength or interpretability hierarchy, where the natural markers are conventional large cardinals preserved by small forcing. Okay, so that's a pretty big realm. Okay, now here's a picture which has of the sort of the situation I've been describing. On the right, we have the scale, a scale of large cardinal axioms. Start with ZFC. Here we have ZFC added with an inaccessible, measurable cardinal above that, some other technical thing there. At the top, and it should be way up, is supercompacts, supercompact cardinals. Okay, now these large cardinal axioms calibrate the consistency strengths of these, in quotes, natural theories. Okay, for ZFC, it's equiconsistent to add Sussman's hypothesis, negation of Sussman's hypothesis, CH, negation of CH, tons of other stuff. And inaccessible, it's equiconsistent. ZFC plus an inaccessible is equiconsistent with some statement. Okay, a really nice one. All projective sets, there's all sets definable in the language of second-order arithmetic of real numbers have this regularity property of being Lebesgue measurable. Okay, and then there's some other ones. Looking way up at the top, supercompacts have been used to show the consistency of many theories. One famous one is something called the proper forcing axiom. We don't actually have an equiconsistency at that level. Although it's conjectured to be equiconsistent, we don't have a proof of that. Okay, and that's because of the basic tools being missing to deal with theories at that level of consistency strength. Okay, so the two tools that one uses to prove these equiconsistencies are forcing in one direction. So forcing will start with an interpretation of the language of set theory where you have one of these large cardinal axioms true, like accessible. Produce a variant interpretation where all projective sets are Lebesgue measurable. So take a model here, produce a model here from it, called the generic extension, where that's true. Okay. The other directions, the reverse directions, take a model here and produce a model here. This is done by the method of inner model theory. Down at this level, the inner model is Gödel's constructible universe L. Okay, so if you take any universe where all projective sets are Lebesgue measurable, look at the constructible sets within that universe, they think that there's an inaccessible cardinal. Okay. The trouble up at the top is inner model theory is much less developed than forcing, basically. We don't have the tools for going in that direction. Surely they exist, but we don't know them right now. Okay. We don't have a theory of canonical inner models at that level. Okay, this is the picture continued. I don't want to spend much time on this, just to say that wooden cardinals, roughly speaking, represent the extent of inner model theory at the present. So we can prove non-trivial equiconsistencies up to around the level of wooden cardinals. And then there's this big gap in these stronger large cardinal notions like superstrongs and supercompacts, which are useful in producing interpretations with natural set theories being true. We don't know how to show they're necessary because we don't know how to get the canonical inner models. So climbing this gap is a big project. And this should let you in on the fact that when I describe this, the natural theories, they're all equiconsistent with natural large cardinals. Well, that's sort of betting on the come to some extent. There's a pattern which is very well developed at these consistency strengths. We suspect it goes further, but we don't know that yet. Principally because inner model theory is not developed well enough. Okay. Okay, now I want to digress, and multiverses have been talked about in this series of workshops. I want to bring in some philosophical comments about what this picture says about multiverses, or how to think about multiverses. Okay, so what does this picture, this sort of well-defined consistency strength hierarchy, which seems to decide all questions about reals and well-behaved sets of reals, what does that say about what we should believe or give preferred development as a framework theory? Well, at one level, you could say it shows there's no big deal because developing one theory develops them all via our interpretation methods. All theories are contained in all other theories of higher consistency strength in some level via the relative interpretations. And at the level of concrete statements, they don't diverge. So isn't this good enough? Well, there's a question of how their theoretical superstructures fit together. That is, we would like to have one framework, one theory where they can all be brought into comparison and used together. You want a way to use them together. So you hear the philosophy, let 1,000 flowers bloom. Well, they should bloom in the same garden. Otherwise, you can't enjoy the beauty of the other guy's flowers. Okay, so we'd like to put the theoretical superstructures together into some common theory, a useful framework. Okay. You can amalgamate theories by interpreting them as speaking of disjoint universes. That's a useless framework. It's not a framework at all. Or you can take some sort of formalist view where you just talk about the theories and rather than how they fit together. Okay, so that's not a framework. You want a useful framework. Okay, now the multiverse idea is, well, let's step back and not commit ourselves to calling one of the, let's see if we can avoid singling out a particular interpretation. Okay, or let's put it this way. Just say it the way I said it here. Calling one theory the theory of V, and the other theories of generic extensions of V, may have no rational basis. That is, there may be no way to choose. So let's ask, can we avoid doing that and yet have a foundation for mathematics? Okay, so basically what I'm going to do is cut back the standard language of set theory so that you no longer can refer to V. Okay? And whether or not one should go beyond this cutback language can then be a question for us to consider. Okay? But let's at least look at the cutback language. Okay, now any proposed foundation should have a language and a formal theory stated in that language. That's what a foundation is. Okay, so what would be the multiverse language and what would be the multiverse theory? Okay, so the multiverse language I'll describe, and an open-ended multiverse theory. I'll describe it in a formal way, but it's routine to formalize this. Completely routine. Okay, the language, we may as well use the usual syntax of set theory, but let's have two sorts of objects, one for the worlds and one for the sets. We can define the worlds as the proper classes, the sets that don't belong to each other, but let's just, for simplicity, we'll have two sorts, worlds and sets. Okay, and here are the axioms for the theory. First, for every axiom phi of ZFC, we say that every world satisfies phi. Okay, and we say that for all the large cardinal axioms we're smart enough to find too. Large cardinals are preserved by small forces. Okay. Okay, so all the worlds satisfy ZFC and the large cardinals. And then what are the worlds? Well, the worlds are, every world is a transitive property class. If W is a world and P is a poset in W, then there is a world of the form WG where G is P generic over W. That is, all the set generic extensions of every world, sorry, for every world in every notion of forcing, there is another world, which is the generic extension. Okay. Further, you can go inward. That is, if U is a world and W is a generic extension of it, sorry, if U is a world and it's a generic extension of W, then W is a world. And finally, amalgamation. If U and W are worlds, then they can be put together into a single world. There's a common generic extension of the two. Okay, so that's the theory. That's the axioms of the multiverse theory. This has nothing to do with Joel Hampkin's multiverse, which it's also not Hugh Wooden's generic multiverse. That's closer, but it doesn't have generic extension. Sorry, it doesn't have amalgamation. Too many things go into that multiverse. Neither Hampkin's nor Wooden's theories were presented in terms of a formal language and a theory in that language. So it's not clear there was a foundation there, a proposed foundation. Okay, the natural way to get a model of the multiverse theory out of an ordinary model of ZFC is the following. Basically, we do all of the set forcing that you can do. That is, we collapse every ordinal of the ground model M to be countable, and then look at all of the worlds that you can get to. Look at all the generic extensions by set size of initial segments of that G, and then all the worlds that they come from. Okay, so let me not dwell on that on the technical way. That's the natural model. So there is a natural model. Take any model of ZFC. There's a model of the multiverse theory inside that model. That model, in fact, knows the whole theory of its multiverse. So the multiverse theory is part of the theory of the individual universe. But it's not the whole, because the individual universe knows itself. In the multiverse theory, there's no clear reason why you should be able to define, in the multiverse language, there's no clear reason why you should be able to define any particular world. Okay, so we sort of remove the origin. Here are four theses. The weak relativist thesis is that all mathematics done to date can be expressed in the multiverse language, this superficially weaker language, and proved in extensions of the multiverse theory from large cardinal hypotheses. Okay. And I think this is true. I don't know that anyone would disagree with that. All mathematics to date, that's true. Okay, one can go on to claim that this will always be the case, all mathematics, but all mathematics is mathematically meaningless, and let's consider the mathematics we have before us or that we can hope to develop. Okay, so I will not even dignify that claim with a name. Okay, now one can go, here's a stronger relativist thesis. And now that we have the multiverse, what are its properties? What are the properties peculiar to the worlds? In particular, is any world definable? If you have a definable world, you're really back to the standard language. Okay, so the strong relativist thesis says no individual world is definable in the multiverse language. In particular, there would be a natural attempt to define a world that's contained in all the other ones. Okay, it has all of the large cardinals that all the worlds have. Every world's a generic extension of it. It's the root. So does the multiverse have a root? That's a natural question you can ask in the multiverse language. The virtue of the multiverse language is it brings that question to the fore. If there is a root, then surely the theory of the root's really important. Everything else is a generic extension of it. Okay, so if there is a root, call it V if you want. At any rate, there doesn't seem to be a way to distinguish. That possibility from the standard language. Okay, so that's the strong relativist thesis says there is no definable universe. Okay, now we have the negations. So the negation of the strong relativist is the weak absolutist, who says that there are individual worlds definable in the multiverse language. There is a distinguished one, but definable in that language. And then you have the strong absolutist who says there's a distinguished world, period, whether we can define it in that language or not. So V makes sense regardless. Okay, personally I believe the weak relativist thesis that all mathematics done to date can be developed in the multiverse language in extensions of the multiverse theory. I also like Hughes' idea of ultimate L or K, and in that philosophy or in that possibility, weak absolutism is true. There is a root to the multiverse. Okay, so one can hope that the weak absolutist theory thesis is true. They're consistent. So, say in this view, the meaningfulness of statements like CH depends on there being privileged worlds in the multiverse. And whether that's the case is yet to be determined. The multiverse language I've presented is contained in the standard one. I want to emphasize it's not, we've cut back the standard language. We haven't extended it. The generic relativist idea is that it contains the meaningful part of the standard language. So there's a lot of debate about whether CH is a meaningful question, but has a determinate truth value. Without getting into the general problems of theories of meaning, one can, how would you deal with a theory that can, with a language that can make meaningless statements? You'd cut it back. Because you don't want to be able to make meaningless statements, and you can waste your time on meaningless problems. Okay, so you cut it back. Okay, so this cutting back could be, we could cut back to the multiverse language, and that's what the generic relativist is doing. Okay, it's in this respect that Wooden's generic multiverse is not an appropriate model. That is, the theory of that multiverse is not contained in the theory of the individual universes. So it's not really a cutting back, and in fact, it's not really clear what the theory of that universe would be. In the multiverse I've described, the theory of the multiverse as a whole is present in the internal theory of each world. It's not the case for the richer multiverse that you talked about. In fact, it's not clear what the theory of that richer multiverse would be. Okay. Okay, so that's in addition to an earlier version of this talk with some philosophical stuff about multiverses. Let's now look at how there might be a distinguished universe in the multiverse, because this is the really appealing thing. Okay, so this is the vision of ultimate K. It's not yet a reality, it's a vision. Okay, so what does this picture, again, what's the picture say about what we should believe or give preferred development as a framework theory? Okay, and again, developing one theory develops them all via the Boolean valued interpretations. I think it's an interesting philosophical question whether a Boolean valued interpretation counts as an interpretation. And I'd like to discuss that if possible. I mean, I don't, if I'm thinking of a generic extension of the universe, I don't have objects that actually correspond to those. So I can't refer to the objects that this guy's referring to, but I can translate his sentences. So whether that counts as capturing his theory, I don't know. I think so. Okay, at any rate, at the level of concrete sentences, they all just agree with one another. And we do have referring terms. Okay, now there might be a best framework. So nevertheless, there might be a best framework theory or equivalence class of them under intertranslations, a distinguished universe in the multiverse. And the theory of that. Okay, this framework theory would contain a locator axiom, which basically tells you which universe in the or which class of universes in the multiverse you're taking as your reference point. And height axioms, those are the large cardinal axioms. Say there are more and more ranks, more and more ordinals. Okay, the incompleteness of the theory might reside solely in the height axioms. So we always have Gödel-style incompleteness, but that can be resolved by large cardinals. Things like CH are incomplete in the way that large cardinals don't resolve, but CH maybe is resolved by locating yourself in the multiverse. Okay, so such a theory would decide the continuum hypothesis and much more. In fact, it should give a systematic theory of everything. Okay, the best location is the center. And you'll see what I mean in a bit. The center is, at the center is a canonical inner model. Okay, so if you remember our picture, we had the hierarchy of models. We had the hierarchy of large cardinals, and we had all these random theories out there that were natural to set theories. And the models that we got back to from the random theories, those were the canonical inner models. Okay, and then we can go out by forcing out into the wilds, but at the center is the canonical inner models. Okay. Okay, moreover, these models have a global theory that has no counterpart elsewhere. And that is, nothing rivals fine structure theory as a global theory of the universe of sets. The canonical inner models are constructed in a well-ordered hierarchy, like L, where you understand the next step to the extent that it's possible to understand the next step ever. Okay, so the next step is always as small as it could be. And you have a systematic theory of sets based on how they are generated in this hierarchy. We decide not just the continuum hypothesis, but all the many, many other statements that set theorists have investigated. We think, of course, we don't know that complete theory, but we don't think we lack axioms. Okay. There's no candidate locator axiom which produces a detailed global theory of the universe of sets, except those asserting them via some kind of canonical inner model. So the forcing axioms have been propounded as, proposed as leading to a complete theory of subsets of Aleph 1, for example. And they do seem to. But there's no hint of a forcing axiom which goes, which decides GCH or all the other many global questions about the universe of sets. So there really is nothing to rival fine structure theory as a set of tools for systematically deciding questions in general set theory. Okay, so if you can make sense of V as the ultimate core model, ultimate K, and if it and do it in a way that it's compatible with all of the consistency strengths of the large cardinal axioms we've found so far. Rank-to-rank embeddings are basically the strongest. So if you can do that, then this axiom has many virtues as a locator axiom. Okay, here's a little bit of poetry about ultimate K. Okay, in ultimate K, everything there is arranged in a finely grained, harmoniously ordered hierarchy. Some people don't like the picture of a harmoniously ordered universe of that set. They think there should be randomness because the world's random. So, sorry. Okay, in this hierarchy, nothing appears until you're fully ready to understand it. Because everything appears gradually. Each new phenomenon has almost happened a lot of times before that phenomenon happens. Okay, so this is something called the condensation property, which you may know for L. Okay. On the other hand, when you're ready for something to happen, it does happen, which is unlike L. So L reaches a point where it's ready to add something called 0 sharp, the next real number that's not constructible. Okay, there's no reason that it shouldn't be there, but in L you don't put it there. Okay. And the counterpart of that is you can't climb the consistency strength hierarchy in any natural way in extensions of B equals L. Okay. So now, among the things you see in your harmoniously ordered universe are partial orders, which you can force with, and then you can look at the forcing relation for those models, and they may satisfy very interesting theories. Those models, for example, you'll see the theory of worlds satisfying the proper forcing axiom. And those worlds will have the same theory of the concrete as your own. Okay, so you don't lose the rest of the multiverse just because it exists in generic extensions of you. You can use it, and particularly anything you prove about the concrete is just true in your universe. Okay. So what more could you want? Parallel, if we were to show that this next real beyond L does not exist, 0 sharp does not exist, which could happen, then V equals L would become the natural locator axiom. Then all the models of set theory we'd know would be L and its generic extensions. And we might as well study those from the point of view of L. Okay. Okay, now I want to go more deeply into what that ultimate K that we're envisioning is, this canonical inner model at the center. And to do that, I have to go into more depth about the initial segment of the consistency strength hierarchy where we really know how to construct the canonical inner models. Okay, so vision is that this pattern is going to extend all the way up to the top and at supercompacts, but what we can see at the moment is a much smaller initial segment of the consistency strength hierarchy. Okay, so in fact, this initial segment where we understand things well enough to prove non-trivial equiconsistencies is less than or equal to a cardinal, a wooden cardinal, which is a limit of wooden cardinals. So you can have many wooden cardinals, but not too many. Okay, so that's all where we, there are fundamental problems, which are technical problems, which I believe will be solved. But at the moment, this is what we really have a decent theory of as far as canonical inner models goes. Okay, and so now the pattern that has emerged is there are 3 intertwined hierarchies of sets at the center. I'm calling them staircases because they're hierarchies. Things happen in a finely grained, well-ordered way. On the first staircase, the first staircase is the hierarchy of well-behaved sets of reals, basically. which is ordered by something called the wage ordering continuous preimage. So a certain complexity ordering. So it's the wage hierarchy and a canonical model of the axiom of determinacy, or AD. Okay, so that's the first hierarchy. The second two are fine structural hierarchies of two interrelated types of canonical inner model for ZFC. Okay, so the first one, ZF, is a the models in the first hierarchy satisfies AD, so not the axiom of choice. ZF plus AD. ZFC holds in the other two hierarchies. Okay, models in each of these hierarchies see models in the other hierarchies, perhaps through a forcing relation, at levels less than or equal to their own. You can't see upward. You can see something, you can interpret theories equiconsistent with you or of weaker consistency strength. You can't interpret theories of higher consistency strength. That's what as the girdle showed that. Okay? So, if you're on one of the staircases, you can see the other three at your level and everything below. Okay. Now, the thing is, you can't really develop the theory of any at present. We cannot develop the theory of one hierarchy without developing simultaneously the theory of all three. The theories are tightly interwoven with each other. Moreover, we can't prove consistency strength lower bound. So if you remember that, what that means is take a model of your arbitrary natural theory, like saturated ideals or something like that, and recover a canonical inner model with a large cardinal hypothesis that's equiconsistent. Okay, so recover a canonical inner model with a large cardinal hypothesis. Okay, so you can't do that in general without recovering all three. You can't recover a model in one of the three strands without recovering all the models in all three strands. The theories are interwoven. Okay, nevertheless, one of the strands looks better than the others. Well, okay, the AD strand doesn't satisfy the axiom of choice, so it would be hard on people's intuitions if you started telling them the axiom of choice is false. Okay, that doesn't seem so convincing to me as an argument, but there are other reasons why one might suspect that it's one of the other two strands that makes the more natural frame, whose theory is the more natural framework theory. Okay, here's a technical definition of what a well-behaved set is, Hom infinity set. So if you want one technical detailed definition to remember, here it is. Okay, a set A of infinite sequences of natural numbers is called Hom infinity. If you can reduce the question of membership in A to the question of well-foundedness of direct limit systems in a certain way. Namely, for any cardinal kappa, there's a continuous function from infinite sequences of natural numbers into direct limit systems. Continuous means the first n elements of the direct limit system depend on the first n digits in X. Okay, such that the base model of your direct limit system is always V. The models are all closed under kappa sequences. And X is in your set if and only if the direct limit along the system corresponding to X is well-founded. Okay, so basically large cardinals give you enough elementary embeddings that this definition produces all sorts of Hom infinity sets. the more embeddings you can get out of your large cardinals, which is how one uses large cardinals, the more Hom infinity sets you're going to have. Okay, the concept comes from Martin 1968 as one of the basic concepts in the whole subject. That Hom infinity sets are determined, and from that follows that they're Lebesgue measurable, have the property Baire, and all sorts of other regularity properties. That's why Martin came on the concept to prove the pi-1,1 sets are determined, which he did by proving their Hom infinity. Okay, the definition seems to capture what it is about sets of reals that makes them well behaved. It's the fundamental regularity property. Okay, what sets are Hom infinity? Well, if they're arbitrarily large wooden cardinals, then there are lots of Hom infinity sets. For any collection gamma, point class gamma, that's a collection of sets of reals, or subsets of omega to the omega, which is closed under continuous preimages. So for any point class gamma properly contained in that, every set of reals in L of gamma and R is Hom infinity, and therefore L of gamma and R satisfies the full axiom of determinacy. So if we construct from the well-behaved sets of reals up to some proper initial segment of Hom infinity, we get a model of AD. And those are the models of AD that I'm talking about in the staircase 1. Let's see. Now, questions about existence of Hom infinity sets are generically absolute. That is, you can't change their truth by forcing, which is the counter, sort of the abstract meta-mathematical counterpart of those statements are going to be proved by large cardinals. It's the abstract mathematical counterpart, there's no divergence in the sigma 2,1 Hom infinity statements between different theories once their consistency strengths get high enough. Okay, so if this is theorem of Wooden, if they're arbitrarily large Wooden cardinals, then you can't change the truth value of sigma 2,1 Hom infinity statements by set forcing. Okay, now in practice, the generic absoluteness of a class of statements can be proved by reducing them to sigma 2,1 Hom infinity statements. Okay, but you may need more than arbitrarily large Wooden cardinals to do that. So arbitrarily large Wooden cardinal is actually a very weak large cardinal, moderately weak large cardinal axiom. We do have a canonical inner model theory for that hypothesis. The boundary was roughly Wooden limits of Wooden cardinals, which is well beyond arbitrarily large Wooden cardinals. Okay, but in practice, the way one proves, and in order to prove generic absoluteness of some fairly large class of statements, you may need large cardinals beyond arbitrarily large Woodens. Okay, but the way it goes is you use your large cardinal to show that those statements can be translated into sigma 2,1 Hom infinity statements. So you have an abstract theorem that says sigma 2,1 Hom infinity is generically absolute. You can't change the truth by forcing. And then you feed in your large cardinal hypothesis to show some class of statements can be reduced to sigma 2,1 Hom infinity. And you may need very strong large cardinal hypothesis to do this in particular cases. Okay, now let me just skip that remark. Okay, staircase 2 is a hierarchy of now models of ZFC, not models of determinacy. And these are the natural models of sort of generalizations of Gödel's L that people did think of if you're trying to build generalizations of L which satisfy large cardinal hypotheses that are not true in L, like there's a measurable cardinal. So the basic idea is that large cardinal hypotheses assert the existence of elementary embeddings. Those embeddings can be captured by systems of measures called extenders. And the way we build our model is put in an extender capturing the next embedding, whatever the next means. That's spelled out in the theory. Okay? So a pure extender model is the constructible closure of something called a coherent sequence of extenders. An extender is a system of ultrafilters coding an elementary embedding. The extenders in a coherent sequence appear in order of their strength, where one is considered to be stronger than another if, so E is stronger than F if F exists in the target model for E, the range, the ultrapower by E. Okay, so that's the natural strength order. Okay. So that's all I wanted to say. I mean, this is a technical definition that would take several talks. Okay, now, what makes a countable pure extender model canonical is the existence of a certain well-behaved set of reals, a certain Hom infinity set of reals called an iteration strategy for M. Okay, again, for this talk, I should not try to define that. But being canonical has to be a fairly complicated property because the canonical extender models become more and more correct as you go up. So you can't identify them except by properties that become logically more complicated. In fact, canonical extender models become correct at each level of Hom infinity is our guess. So they, okay, so we shouldn't expect to be able to identify them by something in general by something less than a sigma 2(1) over Hom infinity statement. For example, one notion of canonical is well-founded model. That's logically too weak. That's just pi 1, 1. You aren't going to identify models which are sigma 1, 2 correct with a pi 1, 1 condition. Okay, so there's some, anyway, what certifies an extender model as being correct is something called an iteration strategy. That's a set of reals which has to be Hom infinity. Okay. Moreover, it's reasonable to hope that this is the universal form for a sigma 2(1) Hom infinity statement. That is, any sigma 2(1) Hom infinity statement C can be reduced to a statement of form. There's a Hom infinity iteration strategy for a canonical extender model satisfying something associated to C. Part of the evidence of canonical canonicity of these, an extender model is called iterable if it has a Hom infinity iteration strategy. Okay, so it's one of the standard ones. One evidence of canonicity is every real in an iterable extender model is ordinal definable. Okay, and at the moment, we can only construct iteration strategies for canonical extender models at the level of wooden limits of wooden cardinals or a bit past. So that's when I say the intermodel theory is stuck at the level of wooden limits of woodens, that's exactly where it's the sticking point. It's constructing these Hom infinity certificates of being standard models, the iteration strategies. We don't know how to do that.
assuming that they exist, the rest of their fine structure theory, the GCH, condensation properties, all the ways in which they resemble L, works all the way up through super strong cardinals. Remember, at the top of my picture, there were super compact cardinals, not super strongs. Super strongs are close enough, but super compacts were at the top. We don't really know what the extender models look like at the level of super compacts. It's not just that we don't know how to construct iteration strategies. We don't know what their first order form is. And there's some guesses. Hugh has worked on this problem and has some partial results, but basically it's pretty much open. It's open now. We believe there's some generalization of the current form that will go up to super compacts, but that's not done. Okay, so that's the second staircase. Okay, what could be, what's our other canonical model of CFC? Staircase 3. Staircase 3 is going to be the preferred one. Okay, well, what's wrong with staircase 2, the canonical extender models? Well, they can't, if you've taken a canonical extender model which has a wooden cardinal in it, so it satisfies there is a wooden cardinal, it's not too big a hypothesis, then it can't know the reason it's canonical by this theorem. No iterable pure extender model with a wooden cardinal thinks that it's iterable. So it's not really a self-contained point of view to say that you're in an extender model. Because what kind of extender model? There's no, an iterable one, otherwise it's not canonical. But the extender model itself doesn't think that it's iterable. So where's the formal theory that's supposed to be true in the universe V there? If the universe is an extender model with a wooden cardinal, it doesn't think that it's iterable. Okay, so, but the iteration strategy for your extender model is this well-behaved Hom infinity set of reals. It's canonical information itself of a different sort. Okay, so the idea in the third hierarchy is let's start feeding in that information. Don't just feed in the extenders witnessing embedding, which capture embeddings. Feed in the reason why the model is canonical, that is, its iteration strategy. And you'll get something that's more complete. Okay, so here's a pseudo definition. A Hod mouse is a model constructed from a coherent sequence of extenders together with an iteration strategy for the model that's being built. This concept can be made precise for Hod mice having countably many wooden cardinals. So that's well below wooden limits of woodens. The theory of the Hod mice doesn't go as far as the theory of pure LOV models in some sense right now. At any rate, the concept was made precise by Wooden for Hod mice having countably many wooden cardinals. Sargsyan developed it further up to measurable cardinals, which are limits of woodens, and he and I have gone somewhat beyond that, and that's where it stands right now. Here's a little picture of a Hod mouse. There's its hierarchy. There are ordinals at the center. It has wooden cardinals, which are going delta 0, delta 1, delta 2, and on up. And when we pass up to its bottom wooden cardinal, it is just a pure LOV model, at least in the theory we have now. So it's a pure extender model up to its bottom wooden cardinal. Okay, but if we go past that, we have some more information we're going to start feeding in, namely, how do you iterate yourself at that wooden? How do you iterate that initial segment of the model? Okay, so you start feeding in the iteration strategy for the model. Now, let's see, I should say one thing. I explained iteration strategies as sets of reals. What do I mean feeding in a set of reals? Well, what I mean is we look at the generic extension of our model gotten by collapsing delta 0 to be countable. So turn the sets you have into reals by making them countable. Okay? So imagine for a moment that this mouse is actually is truly countable in the universe V. Okay? And has a truly canonical iteration strategy in the universe V. So sigma is a Hom infinity set of V. And now we have our little countable n. Okay, then n can sort of inspect the reals of its generic extensions by collapsing. And we can ask, how does sigma 0 look on those reals? Okay, what we do is we feed into the n the information, we feed that information into n. So it sees sigma 0 by its forcing relation, basically. Okay. Okay, so that's, so you do that, and then the iteration strategies have some condensation properties which mean that the theory, intermodel theory still works. So once we get past delta 0, we start feeding in sigma 0. We also continue feeding in new extenders. So it's both sigma 0 and new extenders to get ourselves up to delta 1, the next wooden cardinal. And then we start telling ourselves how to iterate the model up to delta 1 that we've just built while feeding in new extenders, and so on. And then this goes into the transfinite. At some point, we lose the ability to analyze these models, but up through countably many wooden cardinals, Hugh did it, and Grigor did it a good deal further. Okay. So here are some connections between these three staircases. Okay, from the determinacy staircase, the model, let's assume AD, never mind the plus there. There's a natural extension of the axiom of determinacy that's true in all of the natural models we know about, the ones we get from large, true in Hom infinity. It's called AD plus. Okay. Okay, so if we're in the initial segment of the wage hierarchy, complexity hierarchy on Hom infinity, where we haven't yet reached a model of the theory ADR plus theta is measurable. That's a fairly strong determinacy theory. ADR is determinacy of games where the players are allowed to play real numbers in their individual moves rather than just natural numbers. Okay, so if we haven't reached too far in our AD plus world, then HOD, the hereditarily ordinal definable sets of our universe, is a HOD mouse. Okay? So this shows that the GCH holds in HOD, because you can prove the GCH in HOD mice the way you prove it for L in the end. Okay, so in fact, there's a systematic fine structure theory of HOD mice, like the one for L. Okay, so it was an open question for some time, whether, for a long time, whether the HOD of a determinacy model must satisfy GCH. In fact, it's been revealed it's a canonical inner model, at least in this initial segment of the determinacy models. Your HOD is a canonical inner model, a HOD mouse. Okay. So certainly you can go from the determinacy model to its HOD. That's just a definable submodel, which is a HOD mouse. You can get back to the determinacy models. That is, if for M a determinacy model, HOD of M knows the theory of M. In fact, what HOD does is collapse and look at the generic extension. Let me state it more precisely. If our ground model satisfies ADR plus, that's our determinacy model, it satisfies ADR plus theta's regular, then the ground model is elementarily embeddable into a homogeneous forcing extension of its HOD. So the HOD of the model knows the theory of the model because the forcing is homogeneous, so everything's decided by the empty condition. Okay. So I assume that ADR plus theta's regular is true in the model, just in the ground model, just to make it easier to state the theorem. There's a counterpart for arbitrary AD plus models. So the HOD, in some sense, there's no loss of information when you pass from the determinacy model to its HOD. The HOD knows the theory of the determinacy model. Okay, now getting from either of these, so that's going back and forth between staircase 1, the determinacy staircase, and staircase 3, the HOD-mouse staircase. What about the extender models? How do they fit in? Well, in order to analyze HOD, in order to prove Grigor's theorem, you really need to bring in the extender models. And that's because, as I said, HOD up to its bottom wind cardinal is an extender model. And if you don't prove that, it's really hard to see how you're going to analyze it. I mean, if you really had an analysis, it's going to prove that. Okay. Now, we know that only up to the initial segment that he analyzed, up to the minimal model of ADR plus theta is measurable. Mouse set conjecture says it's true much further. So assuming AD plus, and we haven't gotten all the way up to a Hom infinity set, which is an iteration strategy for a superstrong, that's very high, then HOD is a pure extender model below its Witten cardinal. And then one could go on to attempt to analyze it as a HOD mouse and prove GCH. But it seems one ought to prove this conjecture as part of the analysis. Now you might ask, why the restriction to extender models that haven't reached this iteration strategy for a superstrong? That's a fly in the definitely shouldn't be part of the picture. Well, the reason is technical, namely, as I said, for supercompacts, we don't know what the right first order form of the model is. So I can't, presumably, there are determinacy models which have within them an iteration strategy for a model with a supercompact, whatever that is. The first order theory of the minimal one of those is going to be a canonical real. It will be ordinal definable. Okay? And so it will be in HOD, but it's not going to be in an extender model in the sense that we know of extender models now. So, because they don't reach supercompacts. Okay. So basically, the concept of extender model needs to be properly generalized. And if we do that, then we're going to be able to eliminate the restriction that there's no iterable pure extender model of a superstrong. So this says we're in the region where we know what the extender models look like. Okay. Okay, Sargsyan proved the mouse set conjecture in this region. Okay, let me skip over that.
Okay, let me conclude with, so we have these three staircases. We sort of understand how they're related up to the consistency strengths of a wooden limit of woodens, which is at some intermediate level. I mean, there's definitely at the level of super strongs and super compacts we don't understand, and we just have guesses. But one could hope that the pattern extends. Now, of the three staircases, the Hodde-Mouse staircase seems like the most natural one. First, they're models of ZFC. You have the global fine structure theory, and they are self-contained in a way that the extender models don't seem to be. That is, they know their own iteration strategies. Okay, now, so a candidate axiom is V is a Hodde-Mouse. We like to say that. Okay. Now, we aren't going to be able to say it in that form because we don't know what the pure extender models look like at high enough. So we can't say it's a Hodde-Mouse. But we can say right now, V is the Hodde of a determinacy model. V looks like the Hodde of a determinacy model, whatever that. Because we do have Hom infinity makes perfect sense in generality. Okay, so the determinacy models given by Hom infinity ought to go all the way. Our pure extender models, we don't really know how they go all the way. But once we have the determinacy models going all the way, we have their Hoddes going all the way. Now let's just say V looks like the Hodde of a canonical determinacy model. V looks like the Hodde of Hom infinity. Okay? That then should pin down, that should be the axiom which pins down a theory for V, consistent with all the large cardinals. And then it's our job to analyze that Hodde, improve, that it satisfies GCH and all that, and that's going to involve Hodde-Mice and all the rest of it. Okay, but we can sort of state now an axiom. Okay, so here's one form of it. In this form, it's helpful to add some large cardinal hypotheses. So I'll say there's a strong cardinal, and they're arbitrarily large wooden cardinals. Okay, and if kappa is the least strong cardinal, then I'm going to say, what does V kappa look like? I should say, if kappa is strong, then V kappa is a sigma 2 elementary submodel of V. So you're really saying what V looks like in some sense all the way. For example, if GCH holds below kappa, then it holds everywhere. Okay. Okay, so what do we say about V kappa? That there's an elementary embedding from it into the Hodde of a certain determinacy model that it can see through a forcing relation. Okay, well, I guess that I didn't say anything more than that. Okay, so it's the Hodde up to theta, which is the length of the wage hierarchy. I guess one point here is this M, which is the derived model of V at kappa, that's a homogeneous forcing extension of V. But because it's homogeneous, the Hodde of that model is in V. It's not some collection of imaginary sets. Those are real sets in V. And J itself will be in V as well. So this imaginary universe M just serves to identify two proper classes in V, J and that Hodde. Right? That Hodde is actually a set, I guess. So it's two sets in V. It identifies two sets. Okay, so this is a proposal. Basically, it's a variant of Hugh's proposal, but it's just the same idea. Okay, this
this, oh, how does this fit with the multiverse picture? Well, Hugh has proved that the Hod of a model of ADR plus theta regular is the root of its own multiverse. So in this picture, if this is the axiom, the multiverse is going to look like you're at its root, okay, which is, I think, a nice feature. Okay, let's see. Let me just, there are some variant axioms saying that you're on other staircases that I won't go into. So I think this one is the most promising. Okay, so to conclude. So by now, philosophy has outrun the math, and the math has outrun the philosophy, and they're all running circles around each other. At any rate, here are some open problems. So there was a lot of speculation here. Basic questions include how iterable is V? What kinds of iteration strategy, can we construct iteration strategies for V? Or for mice with canonical intermodels with various large cardinals up at the level past wooden limits of woodens. So solve the iterability problem. Are there iterable pure extender models having superstrongs? Or even weaker than that would be something called measurable woodens, which looks like a significant target. Stronger than that would be supercompacts, but then we have to extend the meaning of extender model somehow. Okay, so, let's see. Okay, now this picture that V is a Hod mouse, that axiom at the end, that you look like the Hod of a determinacy model, that's meant to be consistent with all the large cardinal axioms. What led Hugh to propose it in part was that Grigor found an error in some earlier thing that, so it's the possibility that there could be models with Hod mice with arbitrarily large cardinals that leads to this hope in this picture. But we don't, in fact, know that. So we don't know how to construct Hod mice with wooden limits of wooden cardinals. Okay? And that's a basic test of this, this picture. Can you do that? Okay. Related to that is, can you prove the mouse set conjecture, which is a basic ingredient in analyzing the Hod of determinacy models, is to prove that every ordinal definable real belongs to a canonical extender model. Okay, there are things to do with measuring consistency strengths up at the level that I said we didn't know how to do it. I haven't emphasized that, so let me skip over. Just say that in some sense, a proof that con PFA implies con supercompacts would take all of the elements of everything that I've talked about and put them together, solve basically all the problems I've talked about would have to be solved to do that. So in some sense, that's the peak that's way off there. That if you can climb that one, you're going to have to climb all the other ones along the way. Okay? And I guess the second thing to say about that is it's an arithmetic question. Is there a proof in Peon arithmetic? That's a sigma 1 question. So, okay, so nobody can say that's a meaningless question unless they are an ultra-finitist or something. Okay, and most basic, what's up there? Okay.
Questions?
sequences and things are just out somewhere else. And even long extenders are not in this picture. So can you extend the staircase by at least some kind of analogy, assuming these things are around in some way?
Well,
these extended, not pure models, but
okay, so the suitable extender sequences were Hugh's, they're Hugh's attempt to generalize the notion of pure extender model so that you can have super compacts in your pure extender models. So they can satisfy there exists a super compact cardinal. And to do that, one needs to add not just, I mean, I never defined extender, so you're not going to know what the difference between a short and a long extender is. But anyway, we have a theory for something called short extenders, and you have to extend this theory to something called long extenders, and then build a canonical model where you have these long extenders. The suitable extender sequences was an attempt to do this. You can build models, but he showed at some point that these models are not canonical. That is, there are suitable extender models that have all the reals in them. So that was a development like a year or two ago. And so one really needs, and it was because he was what he was attempting to do. I don't know if you, how much we should go into the details, but he was attempting to avoid the full fine structure theory for the intermodels. Okay, so in the past, it's been possible to develop a sort of an approximate intermodal theory. Like the original theory of L of U is an approximate intermodal theory because there's no fine structure for that model. Okay, and Martin and I did something like that for intermodals with wooden cardinals later on. Okay, so you can get approximate intermodal theory down at the bottom without going all the way to a full fine structural analysis of the hierarchy step by step. And he was trying to do something like that at the level of supercompacts. And the thing is, if you generalize these, call them coarse intermodals, the approximate theory in the way that he was led to, the models are no longer canonical. You can't distinguish them from V. Okay, so one really needs to do the fine structure theory from the beginning. And that's what he's working on. I mean, that's an open project.
Any other questions?
Yes. I'm Peter Koellner, doctor of mathematics. I'm not a specialist in set theory hierarchy, but my questions were inspired by the term well-behaved, which you have used a couple of times.
Yep.
The question is the piano arithmetic behavior well behaved because it is inverse with respect to the extension comparing with the other theories. Second one. Second phenomenon. And next question, why it has this behavior? Last question, is it the only one arithmetic theory with this kind of behavior? Thank you.
So the question, let me first say, my adjective well-behaved for these sets of reals is not meant to have an exact significance. And so let me explain that before I turn to your question whether piano arithmetic, is it the natural numbers that are well-behaved or the theory itself?
Yeah, theory.
You're asking about the theory itself. Okay. So I was using the adjective to apply to sets, certain sets of reals, and it comes from classical descriptive set theory. So around 1900, Borel, Baer, and Lebesgue had the idea that although they accepted Cantor's theory and there's well-ordering of the reals, and therefore there are ill-behaved sets of reals that are, say, not Lebesgue measurable, don't have the Baer property, don't have various properties that make them amenable to being dealt with in analysis. So there are these ill-behaved or pathological sets of reals out there. Nevertheless, there are plenty of well-behaved ones, and why don't we focus on them? Okay, and in particular, the Borel sets of reals were introduced at that time, and they proved all sorts of nice structural properties. Okay, so in some way, the Hom infinity sets are the ultimate generalization of the Borel sets in that form. In fact, there's some alternate definition called universally Baer, which you may have encountered, which is equivalent in the presence of wooden cardinals. So if you, assuming an arbitrarily large wooden cardinals, the set's universally Baer if and only if a Hom infinity. And universally Baer just says you are a Borel in a certain sense. You have a representation like the Borel sets have, an absolute pair of trees that project complements absolutely. It's just that the trees can now be uncountable instead of countable. At any rate, so Hom infinity is a notion of, well, good behavior that extends the classical notion of Borel, and the good behavior means amenable to techniques of analysis. Let's see, I'm not sure what it means for a theory of the natural numbers to be well behaved. I guess that, let's see, I believe that it only proves true things, so that's an important good behavior. That everything that it proves is true. It doesn't prove them all. That's a lack, but then it's a lack that we can't ever avoid. There are interesting questions about the natural numbers which are independent of Peano arithmetic. To my knowledge, I'm not sure whether it's been verified that Fermat's last theorem follows from Peano arithmetic. So in some sense, Peano arithmetic is not well behaved as an environment for which, as a theory of all mathematics, because there are plenty of things beyond the natural numbers to think about, and they have consequences for the natural numbers. I'm not sure if I've answered your question.
Is the only one?
Well, okay. So one thing that this picture that I started out with is that we don't have divergent arithmetics the way we have divergent set theories. That is, all theories, all set theories, and actually this extends just to extensions of Peano arithmetic that have been concocted with some independent idea to them, agree with one another in their arithmetic consequences. In fact, they're well ordered by inclusion in the arithmetic consequences. So there's one theory of the concrete that's common to all of these natural theories. And Peano arithmetic's part of it, but there's all sorts of stronger statements that are in it too. Okay, so I don't know if this answers your question, but there isn't an alternative to Peano arithmetic, or there's no alternative to the arithmetic that we get out of measurable cardinals, which is definitely stronger than Peano arithmetic, or the arithmetic we get out of rank-to-rank embeddings. There's no alternative to it. You can refuse to embrace it, but no one's proposed an alternative.
Thank you.
Yeah.
There may, however, be what you might call a nightmare scenario which climbs equally high into the hierarchy. let's see, if you recall Giddick's consistency using a proper class of supercompacts, in which every single cardinal is cofinality omega, and other. I think I've seen stuff where they talk about not just the cardinals, but the power sets of cardinals and stuff. Those things clearly are, well, I mean, they certainly required very strong axioms to get them, and you might think that they might also give very strong axioms, even though from anybody who looks, even that determinacy is as pretty far out there, this one's really a nightmare. But
yes,
it may not be the only other way to climb this hierarchy.
Yeah, well, I think what you say points out how unnatural the natural theories can be. That is, set theorists are pretty Catholic in their willingness to consider various scenarios. And yeah, I mean, every cardinal has cofinality omega. That is a natural enough statement, right? I mean, why not think about that? And one can, I mean, I don't think the consistency strength of that particular Giddick statement has been pinned down exactly, but someday someone will do it.
It's been weakened to a proper class of strong compacts, which certainly, but still it seems pretty strong, and as you go to similar statements about the power sets of cardinals, it could get stronger.
Well, that's a good example then, because we have no hope of an equiconsistency if it's as strong compacts, because strong compacts are, one believes, equiconsistent with supercompacts. That's yet to be proved because we don't have intermodel theory for supercompacts. But presumably this is another statement up at the level of consistency strength of supercompacts, and until intermodel theory reaches that, we won't be able to do the reversal.
I think unfortunately we're out of time, but let's thank our speaker.